Okay, so this is video 4 on waves, intervals, and segments. So in order to really get a good interpretation of your ECG, you have to understand a little bit more about the waves, the intervals, and the segments that you're going to see as part of your EKG. Now here I have one heartbeat or one cardiac cycle where we have the P, the QRS complex, and the T wave. So we have atria depolarized, the ventricles depolarized, and then the ventricles repolarized. So let's just take another look at our heart with our electrodes placed, and the negative is up here next to the right arm. This positive electrode's down here next towards the left leg, and our AV or SA node fired, depolarized the atria. Here's your depolarization. You got your P wave that traveled to the AV node, down the bundle of His, the right and left bundle branches, Purkinje fibers, and the ventricles depolarized QRS complex, and then you got your T wave. Right? So if we go back and we look at when the atria depolarized and we look at the P wave, something you want to think about is how long should it take for that depolarization to cross the atria and for us to get our P wave? How wide should that P wave be? Because if this takes too long, that might tell us that our atria are enlarged and there might be something wrong with this individual. So a normal P wave is typically less than 120 milliseconds. Okay, but that, just to make that a little bit easier, that's 0.12 seconds. So how many small boxes is that? A small box is 0.04 seconds. So a P wave should essentially be less than 3 small boxes. All right, so that makes that easy to look at. So if we have a P wave, we simply start at the beginning of that P wave and go to the end of it, and we see, well, how many small boxes were there from beginning to end? In this situation, there were 2 small boxes. So this P wave lasted 0.08 seconds. And so that's a good P wave. All right. It's also important to know that it shouldn't be too tall. If it's too tall, maybe the right atrium is a little bit bigger than it should be. So it also has a height requirement. It should be less than 2.5 small boxes in height as well. And so that would tell you that the right and left atrium are of the correct size and the depolarization is traveling as quickly as it should be. All right, so that's the P wave. So what's the next part of this cardiac cycle, this P, Q, or ST that's of importance? So we did the P wave already. So the next portion of this is what we call the PR interval. The PR interval. Now, something I should point out is that an interval contains a wave, whereas a segment has no waves. And I'll show you what that means here in a second. So we'll draw our cardiac cycle, our heartbeat. There's a P, our QRS complex, and our T wave. So the PR interval goes from the beginning of the P wave to the beginning of the QRS complex. So beginning of the P wave to the beginning of the QRS complex. I misspelled my beginning, QRS complex. So what the PR interval represents is the time for atrial depolarization and for the electrical activity to get to the ventricles. Or another way to say it is for the electrical activity to get through the AV node, the bundle of His, the bundle branches, and the Purkinje fibers. All right, so if there's something going on with the PR interval, there's probably something going on with the conduction, probably through the AV node. So the PR interval, there's a certain duration, there's a certain amount of time it should take for that electrical activity to come through the atria and get through the AV node to the ventricles. So a PR interval generally should last between 0.12 to 0.20 seconds. That is 3 to 5 small boxes. So if we use our same example, we said our P wave happened to be 2 small boxes. And so if we keep it that, then our PR interval here was just about 4 small boxes. So it took about 0.16 seconds, that's 4 small boxes, each one at 0.04 seconds long. It took about 0.16 seconds for the electrical activity to go from the SA node all the way to the ventricles. And that's a normal PR interval. So now that electrical activity enters the ventricles and the ventricles contract, and we get that QRS complex. All right, so we got our QRS complex. Now what's interesting, and it's important to remember, is when that electrical activity came down the bundle of His into the right and left bundle branches and off those Purkinje fibers, the electrical activity is essentially depolarizing both the left and right ventricles simultaneously. So the right ventricle and the left ventricle depolarize simultaneously. Because that's a lot of muscle tissue to be depolarizing, and it would take a long time to go from one side to the other. But if both sides depolarize at the same time, that really shortens how long it takes to contract the ventricles. So the duration of the QRS complex is actually fairly short. It should be less than 0.0 seconds, 0.10 seconds. That's less than 2.5 small boxes. So if we looked at that QRS complex, we would start at the very beginning of the Q wave, so right when that line starts to drop, and we go to the end of the S wave, which would be right there. And then we'd measure how many boxes this happens to be, and we'll just say that this one is 3 small boxes. And that's just right on the edge. That's probably considered just a little bit wide. We'd want to see 2.5 small boxes or less in terms of duration to be considered normal. Right? But there's something else we should know about the QRS complex, because this isn't always as easy as it seems. When we look at a QRS complex, and I'll draw my typical complex here, Q, R, S. The Q wave, we call this a Q wave because it's the first negative deflection in the complex. The first negative deflection. And then the R wave is named because it's the first positive deflection in the complex. And then we know which one's the S wave. And pay attention here, because it's the first negative deflection that follows the first positive deflection, or the R wave. So let's look at some examples so this makes a little bit more sense. So what happens if we have this scenario where there's no electrical activity and all of a sudden there's a positive deflection and a negative deflection? Well, what do we name these waves? Well, this is the first positive deflection, so we call it an R. And this is the first negative deflection that follows the first positive, so it's an S. So there is no Q wave here. Well, what if we had this? The opposite scenario. Well, we have the first negative deflection, so this is a Q, and the first positive deflection, so that's an R. If you had this scenario for your QRS complex, well, that's simply a Q wave, sometimes called a QS. because it's just a negative deflection. And in the scenarios we were looking at when we were talking about heart rates, what if it was just like this? There is no negative deflections. Well, that's simply just an R wave. There is one more wave you should know about, typically called R prime. R prime. This is the second positive deflection. And this is important when we talk about bundle branch blocks. It comes in handy. So what would that look like? Let's say we had this scenario. And I'm losing, there we go. So in this scenario, if this was your QRS complex, your first negative deflection is a Q, your first positive deflection is an R, your first negative deflection to follow the positive is an S, and then your second positive deflection is an R prime. So there may be occasions where that happens. So that's the QRS complex, right? Regardless of its formation and how it looks, it should be less than 2.5 small boxes, or 0.10 seconds. Now, if you're looking at your ECG, your typical ECG here, we had our P wave, we had our PR interval, we'll call it a PRI, we had our QRS complex from the Q to the S here. Well, the next important part of this cardiac cycle is what we call the ST segment. So remember, a segment does not contain a wave. So the ST segment is from the end of the S to the beginning of the T. There should be no waves there. So end of S wave to beginning of T wave. So let me draw another QRS complex and T wave here. So the question is, if this is the S wave, where does it end? Well, it ends right here. What you're looking for is, when does that S wave change direction? So it's going to come up towards what we call the baseline here. So I can draw that in another color. Maybe that'll help. So we have a baseline where there's no electrical activity, where the ECG should always come back to. So when the S wave comes back to baseline, or when it changes direction, so here it's just going straight up, that's the end of the S wave. And then the beginning of the T wave is usually fairly obvious right before the T wave starts. And so that would be your ST segment. Now, it could be a little more confusing. You could see this. And so you can see our baseline here has not changed much. Here's our baseline. But what you notice here is the S wave came up, and then right here, it changed directions. And that is the end of the S wave. And we call the end of the S wave the J point. And that is the J point. So if you were to measure this ST segment, you would measure it from the J point. It would be measured from here to the beginning of your T wave. And that would be the ST segment in this position. And the ST segment is incredibly important. The ST segment, as we'll see and we'll talk about many times, is where we measure ischemia. And is there a blockage in the heart resulting in a lack of blood flow and oxygen to the myocardium, resulting in ischemia? And the ST segment can tell us this. So what we're looking for, if it is ischemia, it is actually called ST segment depression. I'll just put an arrow pointing down. The ST segment is depressed. So a normal ST segment is like in this first scenario. I'll put a number 1 over here. Scenario number 1, the S wave comes up to baseline fairly quickly in a flat before the T wave. Scenario number 2 may be an issue. What we need to do is measure it and see, is this not normal? So to have what we call ST segment depression, and which is ischemia. That might be 1S or 2. Where's my notes? Depression, 2. There's 2 S's in there. So ST segment depression. What the criteria for that is, you need greater than equal to 1 millimeter of depression at 0.08 seconds past the J point. So what does that mean? 0.08 seconds happens to be 2 small boxes, or 2 millimeters. So this would be 1 small box, and this one would be 2 small boxes. So let me redraw this and show you the scenario. Here's our PQRS T wave. Here's our baseline. And I'll use even another color here. So what we're looking at here is, here's the J point, right? It's where the S wave suddenly changed direction. So that's the end of our S wave. So that here's our ST segment. So what we're looking at is this ST segment, is it depressed at least 1 small box at 2 small boxes past the J point? So let's go 2 small boxes past the J point. Here's our J point, and let's say this is 2 small boxes right here. So the first thing you do once you identify the J point is you go 2 small boxes to the right, and then you go up to wherever your ECG line is, and that point you're going to say, okay, is that 1 small box below the baseline? So let's draw our boxes, and we'll try and keep them relatively the same here. Okay, so what do we have here? So we had our Q, our S came up, it changed direction, so here's our J point. We're going to go 0.08 seconds, or 2 small boxes to the right, find out where our line is. Here it is. So our question is it at least 1 small box below baseline? And it is. It's almost 2 small boxes. So this is about 2 millimeters below baseline. Whoa. Below baseline. So this would be some significant ST depression and likely be ischemia. This is what we're looking at with the ST segment. All right. So in this video, we identified the waves, the intervals, and segments in a typical cardiac cycle, a PQRST. The P wave has a certain duration, should be less than 3 small boxes. The PR interval should be between 3 and 5 small boxes. The QRS complex should be less than 2.5 small boxes. And then the ST segment should come back up to baseline. If it's more than or equal to 1 millimeter below baseline at 0.08 seconds past the J point, then you have significant ST depression. The T wave itself should be relatively round, symmetrical, and upright in a typical ECG. So that does it for this video.